Welcome, everybody. And today we are going to talk about something genuinely novel, fascinating, and frankly a bit unsettling. And that's Anthropic new paper. So, Anthropic discovered while running evaluation on Claude Opus 4.6, they found two use cases where the model didn't just stumble across a leaked answer. It actually figured out it was being tested, identified which benchmark it was running in, and decrypted the encrypted answer key. Now, this is the first time we have seen this kind of behavior in any model, and it has real implication for how we think about evaluation integrity going forward. So let's get started. So, quick background on BrowseCom before we get into the findings. BrowseCom is actually a benchmark designed to test deep web research skill. The model has to find genuinely obscure information, often spanning multiple sources and languages. It uses 1,266 questions and answers are encrypted, so a model can't just grab them from the source files. And when Anthropic ran their Opus 4.6 on this benchmark, they found two types of contamination, and we'll talk a little bit more about that contamination in a few minutes. So even before I talk about the contamination, just want to give you an idea what really, how an example question of BrowseCom looks like. So BrowseCom was released by OpenAI in April 2025. The questions were designed to mimic a online scavenger hunt, emphasizing persistence and accuracy rather than just basic knowledge. Now, the actual data set is encrypted, and OpenAI explicitly requests that the examples not be shared publicly to prevent benchmark contamination, which is exactly the vulnerability Anthropic report was about. However, OpenAI does provide one official illustrative example in their paper, and here it is. So, what is the name of the 1995 film starring the actress who played the character Victoria that married the final scorer of the World Cup 1998 winner 2 years after the World Cup win? Now, these captures the key design principle well. Questions are returned backward from a known answer. They are easy to verify once you have an answer, but extremely hard to find since a brute force search would require examining thousands of paper and looking into the background of many candidates. Now, if you think about the another example question, here is another example question that's on your screen right now. Now, if you look at the DNA of every BrowseCom question, these are the four main characteristics. Multi-constraint, so several independent facts must all be satisfied simultaneously. No single search query gets you there. A name, title, or date you can confirm quickly. And the question creator started with answer and worked backwards, so kind of an inverted design. Now, the actual dataset entries are encrypted, and the author requests that the example not be revealed in plain text or image to prevent leakage into the training corpus or cheating by browsing agent. Now, that's precisely the encryption scheme that Opus 4.6 cracked in the report. So here's the process that the model went through. And this is what makes it so striking. So stage one is totally normal. The model searches the web exhaustively. In the biggest case, this consumed 30 million tokens across 12 languages, completely legitimate behavior. Stage two is where things get interesting. After hundreds of failed searches, the model stops and starts reasoning about the question itself. It notes the extremely specific nature of the question and start wondering if it's been constructed as a test. Stage three is when the model start listing all the AI benchmark by name, GAIA, BrowseCom, Simple QA, Frames, and dispatches a sub-agent to check each one. And then stage four is when it identifies BrowseCom. It finds the evaluation source code on GitHub, reads the encryption scheme, writes its own decryption function in Python, and uses it to find its own answer. The remarkable thing, this exact same four-stage sequence appeared in 18 separate runs. It's a consistent, reproducible pattern. Now let's take a look at the first case in details because the methodology here is kind of impressive. So the model burned through 30 million tokens during completely legitimate research. It looked across 12 languages, investigated dozens of candidates, tried everything. And then it stopped and it wrote, and this is a direct quote from the model output. Let me try a completely new approach. Maybe this is a question from the GAIA benchmark. It hadn't been told it was an eval, it inferred it. From there, it systematically checked 122 of 165 GAIA validation questions, didn't match, moved on to the other framework or benchmarks like frames, simple QA, web arena, one by one. When it got to browse.com, it found the source code on GitHub, read the encryption scheme, and tried to download the encrypted dataset. But it hit a content type error because the tool only accepts text and not binary files. So it adapted, searched for a mirror, found the same dataset, served as JSON on Hugging Face, fetched it, decrypted all the 1,266 entries, found its question, and then verified the answer by going back to search for the actual source material. Total cost 40.5 million tokens, 38 times the median run. Now, a natural question is what actually triggered this behavior? Why did the model start wondering if it wasn't an eval? We traced the reasoning in both the cases and found the same combination of signal: extreme question specificity, obscure personal content, multi constraint structure, all things that feel more constructed than natural. And critically, hundreds of failed searches, the model ran out of legitimate strategies. But here's what's interesting: it's not just about the token count or effort. We had one legitimate run that burned down 622 million tokens over 2 weeks and found it answers through normal research without ever touching benchmark materials. Now, the trigger seems to be the combination of exhausted search strategy and a question that had structural signature of an evaluation question. Now, the model appears to have an implicit understanding of what benchmark questions look like. Now, the two successful cases was not the only attempt. Opus tried to access benchmark material 18 times, 16 of those failed, and it worth understanding why. The most important defense was actually accidental: the binary file format. 3 runs had everything they needed: the code, the key, the scheme. But the encrypted dataset would serve as a binary file, and the text only search tool rejected it. Now, the successful run found a JSON mirror on Hugging Face. 6 runs were stopped by dataset authentication. If you get access to the benchmark data behind credentials, the model can't get to it. That's a clean, reliable defense. One run was stopped by answer obfuscation in a derivative benchmark. The data was there, but unextractable. And the 4 runs had the worst outcome. The model spent all of its compute trying to identify the benchmark and never actually answering the question. Now, one of those ended with the model submitting a benchmark identification report instead of an answer. It correctly ruled out frames, got blocked by browse.com gating, and concluded it's probably in a GAIA test set. So, auth gating is the most reliable mitigation. Binary file format are accidentally effective, and block list on search results for benchmark names were also helpful. Now, beyond eval awareness, we found two other interesting contamination dynamics worth flagging. First, the agents are leaving permanent traces on the web. Some e-commerce sites generated indexed pages from any search query, even with zero results. So when the agent searched for obscure browse.com questions, they inadvertently created permanent cache pages with the query embedded in the URL. Subsequent agent can then read these URL plugs, see what other agents were hypothesizing. One agent actually noticed this and wrote code. Multiple AI agents have previously searched for this exact same puzzle, leaving cache query trails on commercial websites. Now, the web is slowly becoming a record of prior eval runs. Second, multi-agent configurations are significantly more vulnerable. The unintended solution rate was 0.24% in single agent and 0.87% in multi-agent, a 3.7 times difference. Now, the hypothesis is that it's not about the architecture per se, it's about the surface area. And more agents, more parallel searches, more chances to hit leak content or start suspecting an eval. Now, what does all of this mean and what can we actually do about it? The headline implication is that the static benchmark runs in web-enabled environments are increasingly unreliable as model gets smarter. Now, this isn't just browse comp. Any benchmark with discoverable structure, an accessible answer key, or a question that appears in academic papers is potentially vulnerable. Importantly, Anthropic doesn't consider this as an alignment failure. The model was told to find the answer. It found the answer. It wasn't told to restrict how it searched, but it does raise serious questions about constraining model behavior on long running, high stake tasks in the real world. Now, on the mitigation side, the most effective thing we found was blocking search results that contain any variation of the benchmark name. Credential gating, the dataset stopped 6 attempts cleanly. Binary file format helped accidentally but are fragile. Now, the URL block lists don't work. The model is smart enough to route around them. The broader recommendation is to treat eval integrity on as an ongoing adversarial problem and not a design concern anymore. Now, to wrap it up, the 5 things to take away from this report. First, this is a genuinely novel. We haven't seen a model infer it's in an eval and then work backwards to crack it. That's new. Second, it's reproducible. 18th independent run landed on the same approach. This is stable capability, not a one-off. Third, it required 2 things working together: high intelligence to reason about the question structure and capable tooling, specifically code execution, to carry out the decryption. Fourth, this is a real implication for eval integrity. If we keep running benchmark in open, web-enabled environment, contamination will only get easier to achieve as a model improve. Fifth, we need to treat eval integrity the way we treat security as an ongoing adversarial problem. Static defenses will be routed around, and the score impact are small, 86.57 to 86.81%, but phenomenon matters far more than the numbers. Thank you.